Greetings, folks. Welcome to class number 1 of week 13. We've got some photoelectric and some more early quantum mechanical stuff to do, but before we do that, let's go through and talk a little bit about what's going on. So we've got homework due today. This is homework 7 on special relativity. The SR homework is due today. Please be sure to submit that prior to midnight tonight. Please do remember PHYS is also available. That is up and running, and same deal. Please do that prior to midnight tonight. We'll have a PLC. This will be PLC 13. I'm going to go ahead and say a little earlier than I normally would. Use some time now for final review. So this is actually going to be a final traffic light. That means you're going to want to go back, look at the beginning stuff that we started off with. Final is comprehensive in this class. It's going to start at the thermodynamics that we began with. It'll move into the optics with the rays and the waves, and that will be 50% of what is on the final. The other 50% will be everything since the second celebration, which encompasses all the modern stuff. So we started with special relativity right after celebration 2. We're moving into early quantum mechanics in starting last part of last week plus today, and therefore moving a little bit into that and through the rest of this week. And then we've got weeks 14 and 15 on looking at the more modern formulation. So all of that stuff will be comprising 50%, and then everything prior to celebration 2 is the other 50%. So never a bad time to start and go through and just start refreshing yourself on things that you felt good about, things that you felt not quite so good about, and trying to put those things all into the feel good about box. All right. So I don't have that posted as of this recording, but I will be, I'll be putting that up at some point a little bit later today. So we've got that. We left off last time with the photoelectric effect. And this is the emission of electrons. In other words, it's the establishment of an electric current via a material that absorbs light. And we found out a couple of things about this when we examined the Einstein analysis of this. We found out a couple of things. So let me just write this down. This is the emission of electrons by a material absorbing light. Now, as I was saying, the piece about absorbing the light has to be a particular kind of light. It can't just be any light. All right. Now, what that means is that there is a, in the sense of frequency, there's a minimum frequency. Or if you like to think of it, there's a minimum energy needed in order to get this process started. So if you think about the energy conservation and the energy analysis of this, which I showed you in the last video, the picture of that was the deep well with the water, and then you're cranking the well with the bucket coming up. Okay, so there's a minimum amount of energy necessary, and this goes by the same thing. So if you needed any refresher on that, please go check out week 12 class 3, and hopefully we'll be able to set those straight. So because it's a minimum frequency, Yes, a minimum frequency. There's a minimum amount of energy necessary to get this process started. That implies that there's a maximum wavelength that is involved. And I say that because typically, well, maybe not typically, but we should be able to go back and forth between these two formulations. All right. If you look at the energy conservation of the situation here, we can draw bars to represent the energy that's involved. So the first thing that we'd see is in the initial state, this is the initial energy. In the initial state where I have the initial energy, this is all photon energy. Now, the thing that Einstein brought into play here is not only did he say that the radiation field is quantized and made of photons, and that the energy of a photon was h, the Planck's constant, multiplied by its frequency. He also made it possible for us to do an analysis involving only a single photon. Now, that's a theoretical modeling. Well, this is all theoretical modeling, I suppose. But the point is that for some reason it agrees with reality. So there's very little chance of you actually measuring the characteristics of an individual photon. But with our models of it, we can say, oh, it's got this energy, it does this, and the experiments seem to say this is okay. So this initial energy is all photon energy. So let's say that we're looking only at a single photon, and the photon energy is equal to h times f, f being the frequency. Okay, so suppose here initially the photon has this energy to it, and eventually what's going to happen is we're going to go to a situation where I'm going to take that energy and have it appear in the final state. There is no longer a photon. What we say is that the photon has been absorbed, and the photon no longer exists. It has given up its energy to the electron. What we say is that the electron absorbed it, and the easiest way to think about it, though not technically correct 100%, the easiest thing to think about is photon comes in, electron absorbs photon, electron acquires energy of photon, and electron goes and does stuff. Photon no longer exists, energy now lies with the electron. So with this somewhat admitted falsehood, we go forwards and say, because that energy of the photon was incoming, we needed it to do two things. One of them is to liberate the electron from the material, which costs some amount. We'll say this much, which was the amount that was required just to get the electron out of the material. In some sense, you can think of that as a potential energy. We did, however, denote that as the work function. And whatever was left over would be electron kinetic energy. I say this is left over, but that's only due to the way I think about it, because my first requirement is you have to at least have this much energy in order to get in. To get the electron out of the material and to get the photoelectric process started. If your photon does not have this much energy, okay, in other words, if my initial bar here was only this big, okay, then you might be able to see that that is not enough to start the photoelectric process. That's not enough energy that is necessary to get an electron to move out of the material. And therefore, below this energy, which we call the work function, simply nothing happens. You shine light onto the material, you do not get electrons out. You get photons bouncing off, you get reflection, okay? if it's shiny, say. Mostly we're talking about metals, so yeah. Once your photon energy reaches the work function energy, then you will at least start seeing some absorption and some emission of, absorption of the photons, emission of the electrons. Okay? You crank up past that, and that is what gives them the excess kinetic energy, and that's what allows them to start moving away from the material. And then this electron kinetic energy is ultimately what we can end up measuring via using a stopping potential, all right, or stopping voltage. So the work function is a material property, and we usually deduce this because what we effectively end up measuring is not necessarily the frequency of the light that's incoming, but remember that we typically can easily measure the wavelength of the light. And since these two are equivalent, we can imagine that the energy incoming is a known. We can measure the electron kinetic energy on the outgoing side here, and then knowing those two, we deduce this one, and that's just energy conservation. Okay, so this is measurable from a stopping voltage. And this is completely the electrical analog of riding your bicycle along a flat road, stop pedaling, and then try to coast up a hill. If the hill is exactly the right height, then you'll come to a stop right at the very top. And then you can turn around and go back down, which is kind of the fun part. But the idea behind the stopping voltage is to just get the electrons to give up all their kinetic energy right before they would have gotten collected, and we would have gotten what's called a photocurrent. All right, so it's just before that happens. This is measured by a stopping voltage. Okay, and so what we do is we can write in the conservation of energy exactly in this way. In other words, incoming energy equals work function plus kinetic energy. We rearrange the kinetic energy to give us a stopping voltage, and we can plot those. So when we do that, the stopping potential here versus the frequency. Okay, now if I took my conservation of energy equation and I rearranged it slightly so that I ended up solving for the potential, for the voltage, the stopping voltage is then H divided by E times F minus the work function, which is typically capital Phi divided by E. Now, if we simply use electron volts for all of this, then the E doesn't matter. The E does not end up changing the numerical value of the either the Planck's constant or the work function. It just changes the units so that it works out into volts. All right. In this case, what you would do is you would say, oh, the Planck's constant is 4.14 times 10 to the minus 15 electron volt seconds. But I'm dividing by an E. I would put that over here in the units, and I would drop off those two E's. Okay? Once I did that, I would multiply by the frequency, which would kill off the seconds, and that would leave me with the units of volts. All right? So remember, when you divide by E here, unless you want to make your life harder, you're not actually going to change the number value. You're just going to put it into the units and change it there. Okay? If I put this into a graphical form, what you can imagine is that this looks somewhat like a y equals mx plus b. And therefore, if I consider x to be the frequency, y to be the stopping voltage, as I have done, then the slope of this should in fact be Planck's constant, and the y-intercept, notice it is a negative, will be the work function. So if you'd say, oh, I've got a line here, like this, there's a frequency axis intercept, If I trace this line backwards, you can see that there is a negative y-intercept here, and as we've already pointed out, this must be the work function. If you like, I'll make it negative over if you like. Now, notice I'm keeping the phi over e because I'm trying to match what I wrote here, but know that this is just the work function. It's if it was 2 electron volts to get needed to get an electron out of the material, then this number would be 2 volts instead of 2 electron volts. You're right, the E divides off the word electron, basically. The slope of this line would be your Planck's constant. Slope would equal h over E. But notice that would just be the same number. It would just be Planck's constant in electron volt seconds. And I was getting to this here, this cutoff, this is the cutoff frequency. And as I was mentioning, there is a minimum frequency necessary in order to get the entire process started. This is it. So if you don't supply at least that frequency, then it's not as if you're getting something in here. It's just that nothing's happening. Okay, so let's take a quick look at some examples here where we'll throw a few numbers around. All right, let's begin with, for example, tungsten. Okay, suppose that I have tungsten, and let's imagine that I have the question, what is its work function? Okay, so our goal here is to try and find its work function. Now, what do we know about this? Okay, well, let's suppose that we know a few things. Let's suppose that when I put in a 200 nanometer wavelength, that I measure a particular stopping potential. All right, so at a lambda incoming of 200 nanometers, the stopping voltage necessary is 1.7 volts. Okay. Can we find its work function? Well, we should be able to. Not only that, can we also find, when we found the work function, can we find the cutoff frequency or the cutoff wavelength? Might be more useful. What's the maximum wavelength that I could put in and still barely satisfy a photoelectric effect? All right. Well, we'll get to that in a minute. For right now, let's start with this. I have 200 nanometers incoming and the stopping voltage is 1.7 volts. So with this type of thinking here, you have a couple of different ways of doing things. So if you want to just mechanically grind through it, it certainly is possible to do that. I'm going to show you a little trick here, which is kind of an intermediate step. And you're answering an intermediate question, which is, what is the outgoing maximum kinetic energy of the electrons? Okay. Notice not all the electrons were going to be going the same speed. They're not all going to have the maximum kinetic energy. Some of them will have a little bit less because, some will have slightly less kinetic energy because sometimes the incoming photons can liberate an electron that's bound a little bit more tightly. This work function is the very minimum you need in order to start the photoelectric effect, right? Sometimes you get one that's a little bit more energetically bound, a little more tightly. You can go in and get that one out, but then the consequence of that is you have it moving at a slightly slower kinetic energy as it leaves. So the maximum kinetic energy, okay? Because the stopping voltage takes the complete photocurrent, like that's everything that's coming out of the material. It takes all of those electrons and stops them. That must mean the maximum kinetic energy of the electrons is related to the stopping voltage. So let's do an intermediate step of finding out what is that electron kinetic energy. What is the maximum electron kinetic energy? Which I'll just call Ke max here, if that's all right. What's Ke max? Okay. Now, this gets down to units. It seems like a difficult problem, but in fact, it comes down to units. And it's right back to why we have the electron volt here as a unit. How do I convert a voltage into an energy? Well, I do that by multiplying by a little e on both sides. Okay, if I multiply by little e, I divided it in order to get it to this point, but if I multiplied it back, I would have E, an electron, times a voltage. And that would be the energy the electron has acquired. Therefore, with this voltage, the energy the electron acquires is Ke max is equal to 1.7 EVs. And that's something that you can basically just write down because you know what the voltage is, and therefore you know how to take the voltage and use it as a way to find an energy that an electron would acquire. This is, remember, the definition of the electron volt. It's built for this purpose. The electron volt is the energy that an electron acquires when going through a potential difference, a voltage. Those two, by the way, are interchangeable, potential difference and voltage. They mean the same thing, and I'm sorry that I sometimes switch them. If you haven't had 4B, then don't worry, you'll one day realize that's okay, but sorry if I'm mixing up things here. The voltage that you are applying to, say, these two plates, I'm going to accelerate electrons. The maximum kinetic energy that they acquire is the voltage between the plates, because that's the potential energy. This voltage is related to the potential energy that they experience a decrease in, and therefore that's an increase in their overall kinetic energy. So if you know the stopping potential, well, stopping voltage, then you know the kinetic energy maximum of the electrons, okay? If we know this, then we can go back to the total energy conservation equation, which was that the photon energy, which we should be able to calculate in this case, is equal to work function plus Ke max. And that means, since we're looking for the work function, we're going to flop that over to the other side. Work function, remember, is this capital Phi symbol here. So capital Phi is going to then be photon energy minus the Ke max. Photon energy I'm going to use the hc over lambda for the photon energy because we were given the lambda. Certainly I could take this, convert it into a frequency, and then use h times the frequency here, but I find it's nicer to just do this step because remember, hc is a number that's really easily remembered. Hopefully it's easily remembered. And it is 1240 electron volt nanometers. Okay, so basically it's 1240 eV nanometers to find the work function. I'm going to take 1240 eV nanometers, divide by 200 nanometers, and subtract off the maximum kinetic energy. Oops, the maximum kinetic energy we know, so I'm not going to write it as maximum Ke. I'm going to write it as 1.7 EVs. Okay, so in this case, I'm going to have a cancellation of the nanometers. I'm going to get EVs minus EVs, so that's a good sign. And I'm going to be able to get a work function out in electron volts. Alrighty, so let's see, 1240 divided by 200, so that goes away, and then 0.4 goes here, and a 0 goes away, so it's 12.4 minus 2, which is 6.2. 6.2 minus 1.7 is 4.5. It's about 4.5. So the work function is around 4.5 EVs. For tungsten. Let's calculate what it would be the cutoff wavelength for this. Okay, the cutoff wavelength, in other words, the maximum wavelength, right? You can think minimum energy and minimum frequency, and then you can go to maximum wavelength. Maybe that helps. The cutoff wavelength, if I just wanted to barely start photoelectric effect in tungsten, what wavelength would I need? Well, if I go back to this situation here, this is my energy equation, basically, right? Incoming energy equals what you might consider an increase in the potential energy and then a kinetic energy, right? That helps us kind of connect it with 4A mechanical ideas. Now, I have no kinetic energy left. I have nothing to put into this bin if I'm at the cutoff wavelength, right? So the tip off here is I'm putting in just enough energy to get electrons out, and I'm not giving them any opportunity for leftovers, okay? So this is the meal that is the exact right amount, and you eat it and you go, I don't need any more. And they come in and say, we want dessert. No, because I need to save money and not pay for these overpriced postres. So I'm gonna say work function equals photon energy here, and I'm gonna have cutoff wavelength be equal to hc over lambda, and therefore that cutoff is hc divided by the work function. Once again, this number being 1240. And we divide 1240 by 4.5. Like so. What would you get if you did that? I don't actually remember. It's going to be around, let's see, maybe I wrote this down. Oh, I did. It's about 275. Is that about right? Something like that. Let's say it's around 275. Around 275 nanometers, which you know has to be an okay answer because it's greater than what we were putting in here, and this was kicking out some electrons with leftover kinetic energies, okay? So the cutoff wavelength has to be greater than this. If we said, we used 200 nanometer wavelength and nothing happened, well then the cutoff wavelength should be below that, right? It should be below 200 nanometers if nothing happened. So I'd be able to make an assessment. I would know that 275 would be the wrong way to go. I would need something like 175 in that case. But in this case, we did know 200 gave us a stopping voltage of 1.7 volts. So the extra energy here that they came out with, I'm just going to take that away, right? And I'm going to take it away from my photons and say that's going to be the minimum energy necessary, or that's the wavelength that gives me the minimum energy necessary to get the photoelectric effect started. Let's do another example here where we do the reverse. Okay, let's suppose that we know the work function and we're interested in what the cutoff frequency is, or the cutoff wavelength is, and also what stopping potentials we would need for different incoming energies. So let's just turn the problem around a little bit, look at it from a different way. Let's suppose we'll have a different material this time. Let's use cesium. Cesium has a work function of, say, around 2 EVs. Incidentally, just as a way of something extra to throw in here, this is typical for work functions. 2 electron volts here, 4.5. It's very rare that you're over 10, say, right? The reason is because we're using visible light. Visible light typically has an energy of about 1 to 3 or 4 electron volts. Notice that in the last example I used 200 nanometers, which is well into the UV range, right? And that was a 4.5. That was a 4.5 work function, which means that by the time I get to 275 nanometers, 275, if that is even the right answer, which I don't know if it is, but even at 275, this has an energy of 4.5 EVs. These photons do, right? But this is not visible to us. So visible light is typically between 1 and 3 electron volts. And that's a good rule of thumb when you assess what the work functions. Oh, if I got a work function of 156 EVs, maybe I'd say, let's take another look at the math on that one, okay? Well, so let's go here and let's say the work function is 2 EVs. Let's start off by finding the cutoff wavelength. I will also put in here, we'll also find the frequency here just so you can see that calculation. It is trivial, but I find that perhaps that's okay sometimes. So let's start off by finding this. With a 2 electron volt work function, I already have the cutoff kind of written out right here. So we'll do the same thing. I'll just call it lambda C, if that's okay. Good. And we'll do 1240 divided by 2 for the cutoff wavelength. Okay, once again my EVs go away, I'm left with nanometers, and 1240 divided by 2 is 620. And that is, just in case you need a refresher on the visible spectrum, that would be into the reds. All right, the visible spectrum, 620. Yeah, I'd say that's into the reds. So the visible spectrum is typically 400, which is the blues, into the 500s, which is the greens, into the 600s, which is the reds, and then we cut off about 700. Okay, so we go from about 400 to about 700, and every 100 is a different primary color. So, right, you start off with the blues, you go to the greens, you go to the reds. And if you were taught that the primary colors were something different when you were in grade school, unfortunately, I'm sorry to burst your bubble, the primary colors are red, green, and blue. And that's pretty much what you got from that. So, good luck. We've got this into the reds. If I wanted to convert that into a frequency, I could do that. I would have to do C divided by lambda, and then I would go in and say, all right, I've got 3 times 10 to the 8, and I would do meters per second here, but that seems not like a fun thing. Let's convert it to nanometers per second so that we don't have to do yet another conversion. So let's convert this into nanometers per second. That puts a 17 on the 10, which means that's a pretty big number. I'm going to divide by 620 nanometers, okay? So this turns out to be some number, which is what, in the 5, a little less than 5, about 400 and somethings. But the point here is that you're looking at a huge number, right? This is going to be, and I'm probably kind of making this up a little bit, 362, so it's going to be 1 in 20. 1 in 20 would be 0.05, but it's going to be a little bit less than that. So let's say it's about 4.7 times 10 to the 15th hertz. Okay. The hertz unit, just to refresh your memory on the hertz unit is 1 over seconds, sometimes also written as seconds to the -1. And that is because the nanometers here have canceled out. All right. This is the point being here that this is a horrendously large number, and it's not necessarily one that we're super interested in, but here you go for completeness' sake on that. Let's ask the next question of the stopping voltage at different wavelengths. Let's go to 400. Let's start with a 400. Let's start with 400 nanometers. And then let's start with 300 nanometers as well. Okay, so if we did that, what if we looked at those wavelengths? Said, what's the stopping voltage when I am below the maximum, the cutoff, right, wavelength? I can't put in more than 620, but I'm certainly welcome to put in less than 620 and still have a photoelectric effect happening. All right, so in this case, then my perspective would be, all right, if I go back to the original, way of thinking here, I'm going to put E times delta V stopping. Okay, so this is an energy, and remember, this is energy equal to the kinetic energy where there's a maximum, right? This is the max KE. Numerically, these are the exact same numbers, right? So, well, of course they are, but the voltage is equal to the KE max numerically. So remember, if I have 2 volts necessary to stop it, that's because I have 2 EVs worth of kinetic energy. So what we can do here, since we know the work function, is to assess how much energy does a photon of 400 nanometers carry? What's the energy here? And if I take off what is necessary in order to liberate the electrons, the leftover will be my KE max, and then I'll be able to just go straight to my voltage and my stopping voltage, and there should be no problems. All right, so the photon energy here is, once again, hc over lambda, and that's going to be equal to 1240 over 400, nanometers. So that's going to be 12.4 over 4, which is going to be 3.1. That's 3.1 EVs. And that is in the 400s. So, okay, that's about what we were thinking, right? If I was saying, what did I say? I said between 1 and 3. Well, maybe that's a bit much for that. But anyways, okay. So maybe I underestimated a little bit. So I've got about 3 electron volts here with a 400 nanometer wavelength, and that's the blue. So I guess I'm talking about between 3 and 4 EVs. Okay, I gotta remember that. With 3.1 EVs, I'm going to use 2 to liberate the electrons, leaving me with the 1.1 for the maximum kinetic energy, right? So the KE max is going to be 3.1 minus the 2, which I needed in order to get the electron out of the well. That leaves me with 1.1 EVs. Therefore, my stopping voltage is 1.1 volts. Let me try and write that a little bit bigger here. Okay, so that's that. Same basic procedure here for the 300 nanometer wavelength. You go in here and say I got 1240 divided by 300, so we can go over here. Instead of cutoff and instead of phi, I'm going to do 1240 divided by 300. Oops, and that's going to be not in the EV category, that's going to be the nanometer category. Okay. What's this going to give me? This is going to give me a 4 and a what, 1.33, so this is 4 point, that doesn't seem right. 3, if I go 12.4 divided by 3, and it's going to be 4.01, 4.0, why am I blanking on this? This is 4/3, which is 1.33, so this is 4.133. All right, it's 4.1 EVs. Okay, same basic idea. I'm now going to take 2 EVs off that. Okay, I'm going to subtract the 2 EVs off that. Be left with 2.1 EVs, and that's my kinetic energy maximum, which leads to my voltage. And the voltage is 2.1 volts. All righty. All right, happy days? Great. Let's take a look at another photon process. So one of the things that I've talked about, but really only very briefly, is the idea that we did transition from a wave viewpoint to a kind of stream of particles viewpoint, in the sense that the waves that we were thinking of are better represented by a stream of individual, apparently, photons. But yet we still retain some of the wave character because we use a wavelength in doing the photon energy calculation. So when thinking about transitioning from the wave model into the photon model, what you can do, one of the things you can do, in addition to thinking about a stream of particles instead of a continuous wave, is that you can think of each individual photon as having its own energy, okay? And it's essentially, if it's a monochromatic beam of light, then it's essentially equal to the other photon's energies. And they're all coming on in at the same time. They all kind of they are described by a similar wavelength. And because of that, they also carry momentum. Now, this transition, which I described, the energy is basically getting taken away from the amplitude of the wave and put into the wavelength of it instead. But because of that, the photon carries momentum. Now, from a classical standpoint, this is going to be hard to visualize or interpret or have become part of your being. Now, that may be, but ultimately sometimes, and by the way, yeah, it's a hard thing to kind of work with once you first come to grips with it. Okay, you first introduce with it, it takes a while, right? So classical thinking would tell you that the momentum of a particle, which, by the way, you probably studied a lot of in 4A, right? We would have said the momentum of a particle, P, is mv. So with the photons, you'd say, well, okay, but is there any rest mass to the thing? And you'd say, well, no, there's not really a rest mass. So this m is 0 for a photon. So why is it carrying momentum? Well, it's because I think I can probably best describe this whole process and what's happening this week and what's going to happen for the rest of the class, is that I am going to run out of abilities to draw analogies for you. So when I did that well and the water and the crank and then the thing flying off with the excess kinetic energy, we're getting close to the end of these analogies, because ultimately you'd say, well, and sometimes people ask, right? Light acts like a wave, because it shows wave characteristics. Everything we associate with a wave is going to be interference, it's going to be diffraction, right? It has a wavelength that's measurable. It has all these wave qualities to it. Yet we describe it using a wavelength, but with a particle model. So is it a wave or is it a particle? Well, the answer to that is it's light. And it doesn't get simply classified like that. So one of the things that we're going to do going forwards is you're going to say, well, how can it be that way? Because that's the way it acts, right? And this is how light acts. Light acts wave-ish and particle-ish, and we have parts of both models which fit together pretty well. And we come up with this new way of thinking about it, and it's the way light acts. Light acts like this. And you could say, well, it doesn't act like anything else. Well, okay, maybe not yet, but ultimately we'll see there's kind of a class of things that fit into this bin that's not going to fit into only this one or only this one. We have to create in our minds a different bin, not a subset of these two, which is either a wave or is it a particle. Those are not the only two bins that exist. All right, so the momentum of a particle, you'd say, well, how can light carry momentum when its mass is zero? Well, that's because you're thinking about it's a particle. Okay, so this is not going to work for light. This is classical thinking. We need a modern way of doing it. Now, I'm not sure if you remember, but I think back earlier in the semester, I shined a light onto a what's called a radio vane or something like that. It has black and white sides on it, and a little windmill, and it makes it spin around. So the point is that when it reflects off the white side, it turns the white side a little bit more than the black. So the momentum of the particle bouncing off, right, that momentum shift is twice what it would be if it was just absorbed. Now that is kind of classical thinking, it's vector thinking, but that's okay. That kind of introduced the idea that light carries momentum with it, all right? Light carries energy, and so it also carries momentum. Now, you can get to this. Well, I'm hesitant to show you this because I just crossed that out, but I'll show it to you anyways. And this is kind of how the bridge got made. So if you want to say, okay, we know light carries momentum, how do we figure out what it is? All right, well, okay, suppose that for a minute we wanted to work with this formula, which ultimately we don't, but here's a way of perhaps justifying something to you. We know that if we have light, it travels at light speed, so the V would be C. The mass, you would say, well, we talked a little bit about the Einstein equation, right, that E equals mc squared, therefore m is something like E over c squared, right? And the E, we know is this. Okay, so can we use all of this and find a momentum? Yeah, we kind of can. So we can use P equal to hc over lambda, right? That's the energy. Divide that by c squared. That's like your mass term. Oh, that's hard to say. But we're going to multiply by c here. So ultimately, look what happens. This c squared here, I've got two factors of c on the top. So these two go away with that one, and I'm left just with the h over lambda. So light carries momentum that's h divided by its wavelength. This is pretty horrible. I don't even want to look at that anymore. So if you recall studying mechanics, there's no better use of momentum than during a collision. So let's set up a collision between a photon and an essentially or nearly free electron. Because this is momentum and has a conservation law associated with it, I'll draw an initial and a final picture. All right. This is what a photon looks like. And you can verify that by looking at one under a microscope. And it's going to hit this electron. This picture is vastly simplified, okay? The likelihood of the photon hitting the electron, if it's just one of these and one of those, is almost zero. So let's just assume that we have managed the lucky day phenomenon, and the photon is actually going to hit this electron. So what you will find is that you end up with a couple of different options. Okay, I already discussed option number one, the photon completely misses. Okay, great, so that happens. Now, I will say, in practice, and by the way, this experiment's been done, in practice, the way you get this electron is not because you have a bunch of electrons and you're trying to hit them with a photon. You go, oh, there it is, and you try to hit it. You have a material that has electrons in it, okay? And the electrons are not tightly bound, okay? So this is going to be like a photoelectric effect situation, but on steroids, all right? So this thing comes in, hits an electron within the material, okay? And pops the electron, but the photon keeps going, okay? So it scatters, essentially, the photon. The photon does not get absorbed. It does not die. I don't know, it's never alive in the first place, but it's still there after the collision happens. Okay, so when the collision happens, this is the before picture and the after picture, right? Here's your collision happening here, and this is the after. Now, the photon could, I mentioned it could completely miss the electron. Okay, it could. Let's suppose it hits it. It could be a glancing collision. So the photon comes in, hits the electron, and they both go off like this, okay? The point is here that momentum is going to still be conserved. This is a law that we have, and it seems to be useful, so we'll stick with it. The photon momentum and the electron momentum in the final frame must match what the momentum was in the initial frame. The momentum in the initial frame, hopefully you can see, is basically contained within the photon itself. We'll say the electron is essentially stationary. All right, so it could be a glancing collision like this. It could be a situation where it hits head on and bounces back. So the photon comes in like this, hits, bounces, and the electron gets kicked straight, so there's no 2D motion. It just happens all along a line like that, okay? So let's do this. Let's assume the more general case, which is there's a glancing scatter, such that the photon is now coming up here, like that, and the electron is going down that way like this. Okay? If I imagine applying momentum conservation to this, I would say I had only momentum in the photon initially, and it was directed towards the right. That means that if I take the components of the final photon and the components of the electron and I add their horizontal momentum, that should equal my initial momentum. If I look at the vertical components, then this vertical component of the photon here should in fact be balanced by the vertical component pointing downwards of the momentum of the electron there, okay? This is absolutely no different than a 4A glancing collision, okay? It's just that the photon comes in, hits the electron, so we have to use slightly different thinking about how to calculate what the what the photon momentum is, and ultimately what the electron outgoing kinetic energy is going to be. Because, and we aren't going to explore this, but because this electron could be moving relativistically, right? I could have hit it with so much energy that it's now moving a significant fraction of light speed. We, however, are not going to explore that particular option. Now, if I use momentum conservation, what I'm going to do here is I'm going to define a couple of angles. Typically what we're going to do is we're going to measure the angle of the scattered photon. So I'm going to call this angle here theta. I'm going to call the angle of the electron phi. All right, now the wavelength of the incoming photon was a certain amount. I know what it was, okay? It's called lambda, right? And let's say that this one here is going to be different. I'm going to call it lambda prime. Now, one bit of interesting reasoning you might want to explore is, what do you expect lambda prime to be compared to lambda? It shouldn't be equal to it, right? But is it going to be greater than it, or is it going to be less than? Is lambda prime going to be a larger wavelength or a smaller wavelength compared to the initial wavelength? Maybe think about that one and ruminate while we go forward and do a little momentum conservation. Now, I am going to only sketch this out, and this is, I'm going to write 1 or 2 lines worth of conservation stuff. Well, I guess 3, because we're going to do energy also, but I'm not going to go through solving stuff here. So this is really just a viewpoint that the 4A techniques actually work here. All right, so we're going to use them. I'm going to say that my initial incoming momentum in the horizontal direction was carried by the photon. So let's call this x. Let's define that to be the x direction, and let's go upwards so I have a standard right-hand rule coordinate system. If I use the x going to the right, then my x momentum initially is h divided by lambda, because that's my photon energy, and there's nothing else that carries horizontal momentum. And therefore, in the final state, this should equal the momentum carried by the photon in the horizontal direction, which you can see will be h, divided by lambda prime times the cosine of theta, plus whatever the electron momentum is going to be, times the cosine of phi. I'm just going to leave that as p of the electron times cosine phi. If you like, that could be mv. Right, because the electron, if it's moving non-relativistically, it would be described by this classical momentum idea here. So that could be just mv. If I look at the vertical direction, I would say that I have 0 initially. Nothing moving up or down. I do have those two over there. They should balance. So I should be able to write that h over lambda prime times sine theta minus electron momentum sine phi should equal 0. Finally, I'm going to look at the energy of the situation. And I'm going to say, well, initially I've got photon energy here. So here's a bar worth of photon energy. If you're eagle-eyed, then you would also say, but wait a sec, Einstein would tell us that E equals mc squared here. So because the electron is just present, even if it's not moving, it would contribute a rest energy to the initial energy. True, and then it would also do it in the final case. So I'm going to ignore that rest energy. I'm going to say initially we have photon energy. And in the final state, we've got some photon energy as well as some electron energy. And that's going to show up in the form of kinetic. Electron kinetic energy, photon energy. Oh, I should have put this as lambda. This photon energy is related to lambda prime. Okay. So you can see it's very similar to the photoelectric effect, but instead of having an electron ejected, right, which we would in this case, but the ideas are that this photon energy is so large. This experiment is typically done with X-rays, which have keVs worth of energy, whereas, so thousands, right? Whereas the work functions of typical metals are in the 1 to 2 to 3 to 4 range. So is there a photoelectric effect happening here? Yes. Do we need to think about the work function of the electron as it leaves the material? Should we? I don't know. It's not really going to play a big part. Okay. Is it there? In principle, yes, it is there. So from an energy standpoint, yes, we do need to liberate the electron from the material. Is it significant? No, we're not going to worry about it. So I can set up an energy equation with this that looks very similar to the photoelectric one here that I had before, and that's Hc over lambda equaling Hc over lambda prime plus electron kinetic energy. So I'm just going to put Ke electron here. If it is classical, this would be a 1/2 mv squared. Okay, and if this was a classical, that would be an mv, so it would kind of fall out in the wash. All of these things can be solved simultaneously for angles, right? These angles are not known, theta and phi, we don't know. We don't know, for example, we either know the wavelength of the outgoing photon or we know the speed of the outgoing electron. We got to know one of those in order to find the other one. Or we measure an angle and we don't know the other one, right? There are basically 4 unknowns here and we have 3 equations. So we need to know at least a couple of those things. Well, we need to know one of these 4 unknowns so that we can solve. Okay. I want to show you, if I just have a quick second here, and then we'll go into doing an example of this. I want to show you these plots. Not sure if you can see these or not, but hopefully you can, and if you can't, well, then you won't see them. Over here on the left side, this is a incoming photon energy. If you think of the wavelength here as the horizontal axis and the intensity of the X-ray beam as the vertical axis, then what we're doing is we have a detector set and another detector set that's on an axis, okay? And we're firing X-rays in, just as I showed, we're firing X-rays in at a target, and then we are essentially trying to detect where are the scattered photons. So you can imagine when you hit a target with X-rays, every stuff is flying all over the place, okay? But we just have a detector that we can move to different angles. And when we move it to 0, which is straight across, right, no deflection, then we notice that there's no change in the wavelengths. Basically, this is the straight through, photon missed everything, okay? So the photon wavelength is about 72 nanometers here. 72? No, 71, maybe 70 and a little bit. I'm just trying to get used to that scale. All right, now here in the second picture, theta, it says phi, but theta for us, 45 degrees. So I set my photon detector at 45 degrees. I'm detecting a shift. I'm detecting not just photons of the regular wavelength, but also photons of a slightly, notice, longer wavelength. So that's your answer to that question I asked you. Notice when I go to 90 degrees, which is now I'm taking the detector and I'm putting it up here, the photons are coming in from this direction and scattering straight at 90 degrees, right? At a 90-degree angle, straight upwards, say. Notice what the photon wavelength looks like now. It's a touch over 72.5, okay? And the last one is at 135, and you can see now that wavelength is almost at 75 nanometers. So the wavelength is growing. Reason is the energy is getting lower of the scattered photon. The energy is going into speeding up the electron, okay? So what we have then is a shift in the wavelength. We have a delta wavelength, which is what is showed up here on this thing, okay? So let's go through here and take a look at how to calculate that, all right? Now, like I said, I'm just setting up all the conservation equations here. To solve these, is a good day's work, okay? I'm not gonna lie to you. I'm not gonna do it. You're welcome to. So at the end of the day, what you're gonna come up with is a way to calculate the shift in the wavelength, that delta lambda that you saw in the diagram there. Okay? And this is known as the Compton shift. And the reason it's known as the Compton shift is because this experiment was first carried out in Compton, California. And to great success. No, it wasn't. That's a lie. It was carried out in Chicago by a man by the name of Arthur Compton, and that's why it is known as the Compton shift. So this is the delta lambda, which is lambda prime minus lambda. Remember that the primed wavelength, oh, I erased my picture, but the prime wavelength now has to be larger because that photon carries less energy. Because of that, I'm going to write it over here so that I don't run off the board here. I'm going to give it to you how you'll see it, and then I'm going to modify it so that we can use it. All right, so it turns out to be h over mc. This is the Planck's constant, and m is the mass of the electron. If it's not an electron that's getting scattered, it's the mass of whatever it is that is getting scattered. Okay, so this, in this case, since we're talking about electrons, this is the mass of the electron. Okay, so I have Planck's constant, I have speed of light, and I have the mass of the electron. All right, so I've got that, and now I've got a term here which involves the angle, and this is the theta, which is the angle of the scattered photon. Okay. All right, so this is what is known as the Compton shift. It's a shift in wavelength due to scattering of photons off essentially stationary targets, okay? If you scattered them off protons, well, you'd have a proton mass in here, okay? So that's fine. We're gonna stick with electrons though, just to let you know that. Okay, so I said I'd write it for you the way you'll see it. This is typically the way you're gonna see it. H over mc is a wavelength. It has units of wavelengths. You might want to check that to verify for yourself. And is basically known as the Compton wavelength because it tells you how much the shift is going to be. Now, typically, this is a very, very small number, okay? And I will show you why right now. Here's the way we're going to use it, okay? Here's the way we're going to use it. H divided by mc is a difficult number to calculate. What's a much easier number to calculate is hc and mc squared. So if I put a c on top and a c on bottom, this to me becomes drastically more simple because hc is a number we know. And mc squared is a rest energy. It's the energy of the electron. It's the equivalence energy of the electron. Now, you might not know what that is, but it turns out I do, and that's okay. But the electron mass has now turned into the electron energy, or the rest energy. I'll put rest energy here, of mc squared, and that's a number that's fairly straightforward. It's, we'll do it this way. We'll do this. This is how I always remember it. It's 0.511 MeVs. Right? I told you this last time. It's not 911, it's 511. In fact, you got to call 511 before you dig. No, maybe that's 411. Or no, 411's, anyways, never mind. That's the rest energy of the electron. So when I say this is a typically small shift, look what we're dealing with, okay? So 1240 happens up here, and 500,000 happens down here. So this is basically a number around the order of about 1,000 divided by a number on the order of 500,000, okay? So this is a tiny number. And the reason that it's tiny is because it's in EV nanometers, right? So EV nanometers, I'm gonna get a number that's on the order of 1,000th of a nanometer. That's pretty small. I think you'd agree. Okay, so HC over mc squared for an electron is somewhere on the order of 0.001 nanometers. And that means it's known as a picometer, because that means it's around 10 to the minus 12 of a meter. So there's your next prefix in case you didn't know the pico prefix. Okay, that's a pretty small shift, but nonetheless it can be detected, and Compton detected it in about the 1920s. Okay, and it was his theory that came along. He won him the Nobel Prize in the late 1920s, and he came up with the theory. He did the experiment. He basically did everything, so it has his name on it. I can go through, do a quick example here. Do we have time? No, it doesn't look like we quite have time for this. All right, so tomorrow we'll pick up with, starting with a Compton shift scattering problem. And we will go from there into some more beginning quantum mechanics. These two things, and I'm pointing at these two things, but the two things we've discussed so far, the photoelectric effect and now the Compton shift, are both evidence that is pointing towards light being characterized as a stream of particles, because a wave doesn't go through and hit stuff in the way that this analysis seems to, right? You would not write this for a wave. This is two things hitting each other. This is literally a 4A problem. Right? This is not a wave coming in and impinging upon something and doing something. No, this is just that hit that and it scattered off and did this. So the photoelectric effect initially, and then now a little bit later in time chronologically, the Compton effect happening is really giving a lot of weight to the idea that light is described as a stream of photons. And photons have energy and they have momentum and they move along as if they have no cares in the world, which they probably don't. So we're going to take these ideas and we're going to move into a couple of more kind of foundational experimental results and see what we need to do. How do we need to shift our thinking in order to try and explain the results that are coming out from these new experiments that are being done. All righty, so we'll pick up with this Compton shift tomorrow. Please don't forget, homework is due and quiz is due tonight. Midnight is your time for that. I will get the PLC posted, and I will say have a great rest of your day. Try not to get Compton shifted. That would mean you got a lot of X-rays. All righty, we'll see you next time. Ciao.